Let us continue our discussion on overview of experimental stress analysis. Now we move on to photoelasticity. Right now we will confine our attention only to the physical principle and also bring out you have a transmission arrangement, and this we had seen in the beginning of the lecture also, that you have a 2D model of human femur which is analyzed by transmission photoelasticity, and you also have a reflection arrangement, and the reflection arrangement is useful for prototype analysis. And what you have here is, I have a cantilever beam and I have a hole and I put a coating. The coating has the property of stress strain induced birefringence. So, I can get the fringe patterns like this. So, the basic physics behind photoelasticity is temporary or stress or strain induced birefringence. It's the physical principle used is the phenomenon of temporary, because it does not stay. Once the stresses are removed, this birefringence effect is also removed. So, it is a what you are having is, you have to understand birefringence, all that will come when you understand crystal optics. And what we had seen in the last class was, without getting into crystal optics, you have plotted for the problem of a beam under 4-point bending how the contours of sigma 1 minus sigma 2 will look like. You saw them as horizontal lines and it matched with what you had seen in the experiment. So, what you have here is, the physical principle is stress or strain induced birefringence, which is temporary. The moment I remove the loads, these effects vanish. And you have many developments that have taken place in photoelasticity. The photoelasticity is a very versatile technique like strain gauges, and in fact in 1930s people, when they were developing theory of elasticity, many of those solutions were actually verified by experiments using photoelasticity, and that is what we are going to see. And what you have here is, so you need crystal optics is desirable to appreciate, but we have already said that you can do it by this one. And what you do here is, you use a polarized beam of light for revealing the stress information, and the optics required is fairly simple, and fringes are seen in real time. This is very important. If you go to any one of the experimental technique, for example, if you go to holography, you will have a double exposure. Only after processing you will know how the fringes are. So, you do not have any guidance on, while applying the load, whether the load, the symmetry is maintained, all that you will not be able to know. But with developments with computer based processing, you could make even those techniques in real time. So, when you look at any of the whole field optical techniques, one of the aspects you look forward is it providing fringe information in real time, and photoelasticity does that. And data interpretation to physical parameters is easily possible for thin specimens, and the key point here is under normal incidence. So, that you will have to keep in mind. If you are having a curved object, then what you need to do is, you must immerse it in a liquid which has the same refractive index as that, and ensure that you have normal incidence. See, when you go to the finer aspects of any of the technique, there will be restrictions. So, it is a tool, and how good you use the tool, you get the information. So, whatever the experimental technique you look at, you have to look at its positive aspects as well as its limitation. Within that constraint, you should employ those experimental techniques. And I have mentioned that data interpretation is easy for thin specimen or normal incidence. You will appreciate only when you go to other techniques how difficult the data interpretation is. In this case, it is so simple. We have already seen from solid mechanics point of view that you get sigma 1 minus sigma 2 contours. And this technique has advanced mainly because you have a unique technique called stress freezing, very interesting aspect, and that has made the application of this technique to 3-dimensional industrial problems. Analyzing the problem as a whole is very difficult, and what you do here is you take the advantage of analyzing the problem as a whole. At the same time, from analysis point of view, you still live in 2 dimensions by slicing the model into thin slices. So, what you have here is many industrial problems, whatever the engines that you see across, whatever the nuclear reactors you come across, they have all gone through mandatory 3-dimensional photoelastic analysis. That is why the designs have become perfect, and designers particularly, once the design has stabilized, they would be very hesitant to change anything, because for any changes they would have affected, there would be a history. Once it is optimized and stabilized, they do not want to change it, and in those stages you need very good tools for you to give the pertinent information. If somebody copies your design, that is a different matter, he does not require any test. A person who develops a design from fundamentals, he needs to go through experimental methods, he needs to worry about analytical understanding, he needs to use even numerical technique appropriately and arrive at a final design. And if you look at in early stages, 3-dimensional photoelasticity has played a very significant role, and particularly because of a very interesting phenomena called stress freezing. Now you are being sensitized on what are the possibilities. So, this is what in the case of transmission photoelasticity. On the reflection photoelasticity side, people have also developed a spraying technique to put the birefringent coating on large industrial components. One of the component that people do is aircraft landing gear, which is very huge, and they still do structural optimization based on photoelastic analysis, and this model will typically cover a 2 to 3 story building height. It is not a small model. You are actually working on, suppose they want to develop A380, they would have only rig for the previous version A320 or A330 or A370, and they would use that loading jig to make a 3-dimensional photoelastic model, put a coating and do some structural optimization, then finally develop the landing gear and put it in a loading rig and finally verify. So, it is done for huge problems on one spectrum. On the other spectrum, in dental mechanics, if you find they put a floss, they put a wire which goes round your tooth to hold it in place, those clamps are also analyzed by photoelasticity. So, it is a very small model. On the other hand, you have a very huge aircraft landing gear. So, the range is very vast, and it depends on the user how he uses the technique. And like strain gauges, it is versatile, general purpose stress analysis tool. And when you go to each of the technique, what you will find is there are many branches, because each technique by itself is very vast. If you take photoelasticity, we have looked at only 2 variations, one is transmission photoelasticity, another is reflection photoelasticity. Photoelasticity is always an ideal tool for teaching the field nature of stresses to beginners. And here I must tell you, stress concentration you all know right now. I have a plate with a circular hole, I have a plate with an elliptical hole, and I have a plate with a crack. Now anybody in engineering will know what stress concentration is, but if you look at the history, people had, mathematicians and stress analysis had acrimonious debate. Mathematicians used to say an infinite plate with a small hole is equivalent to a plate without a hole, and only with experimental judgment and other aspects they were able to convince whole lot of things happen the moment I introduce a stress concentration. So, people understood there is something stress concentration which you cannot neglect it, and really when you look at what you find here is I have a uniform stress field if I do not have a hole. The moment I have a hole, the stress field becomes biaxial. It is the stress field is also, the stress magnitudes are very high in this zone and also in this zone. This is one thing. Stress concentration means stress magnitudes increase, that is one thing. Just not that, even the stress field essentially changes. And it was Inglis in 1913 who said that when he analyzed an elliptical hole, he could do that by theory of elasticity. His result showed crack is not innocent and crack is potentially dangerous. That is the time that fracture mechanics has not developed, and a new branch of engineering, fracture mechanics, came into existence once people understood that cracks are more dangerous. And what you see here is, I have a crack, and crack where you have the least amount of material is removed. And suppose I take the load as 6 in all the cases. I have a plate with a circular hole, I have a plate with an elliptical hole, I have a crack, and you do not need to explain. You see very few fringes here, you see slightly more number of fringes here, and you see I have not put that as 6, I put that as 7. When I put it at 6, you have a large number of fringes here. So, if you have an appreciation of looking at fringe information, the density indirectly indicates the stress levels are high. So, for a beginner, you get the field nature, you understand what is stress concentration, and you may wonder, I have an elliptical plate, all these cases are finite geometry, I have a finite width and I have a circular hole. Analytically, what I could do is, I could do an infinite plate with a very small circular hole, and here I will have a polar coordinates to determine the boundary condition on the inner surface, and when I go to elliptical hole, you have elliptic coordinates to specify the boundary condition on the inner surface. At infinity, you could consider it as a large ellipse, you could consider it as a large circle, that is the way you can approach the solution. So, for infinite plate with small circular hole, infinite plate with small elliptical hole, you have analytical solution possible, and this goes by the person who has first solved the problem. You have this as a Kirsch's problem in theory of elasticity, this as Inglis problem, and once you come here, many have contributed. Westergaard's solution is very prominent, Williams' solution is very prominent. So, in theory of elasticity, when they analyze infinite geometry with any one of these defects or cutouts, you have a name attached to those problems. So, photoelasticity is very good to understand stress concentration, to understand the field nature. Without much effort, you are able to get it, and you get a closer picture when I have a look at it like this. Some of you have already made the sketch, and I would like you to make a sketch of it, and the essential features. You have this kind of a fringe field, and you have a fringe field like this, you have fringes forward tilted, and so on and so forth. In this class, we have mainly looked at the elegance of photoelasticity, and we have also seen how effectively the photoelastic fringes can be used as optical comparators. Thank you.